light intensity either along the x-axis or along the y-axis, you might see that they're really reconstructing fully the shape before and after the collision. This is the three-dimensional image of a similar event. Two solitons are moving towards each other, practically head-to-head. This is their interaction, and then they go away, and you might see that they are practically unchanged. They can not only repel each other, they also show some weak attraction. When the impact parameter is larger than half a width of the soliton, then after they collide, they become closer to each other. And these two plots just illustrate that the solitons preserve the same velocity before and after collision, or at least similar velocity. They can slightly be different from each other. This is the movie that demonstrates that the result of collision might be different from just simple interaction and resurrection of the solitons. Here you saw the event when the two annihilate each other. This movie shows how a soliton comes to the defect, interact with it, and then being deflected backwards. So the experimental observations demonstrate that we are dealing with the three-dimensional particle-like excitations, but the mechanism by which they are created is not clear yet. So it cannot be the dielectric anisotropy, it cannot be the anisotropy of the electric conductivity. It must be something else, and one of the plausible mechanisms is the so-called flexoelectric polarization. If you look at this molecule, you might notice that it's not necessarily a rod-like thing. It can be of curved shape, such as banana, and when the director is uniform, then the dipoles of individual molecules are distributed more or less randomly perpendicularly to the director, and they kind of compensate each other. But if you create a deformation, such as this bow-like deformation in the soliton, then because of the shape of the molecules, the dipole moments might form a macroscopic polarization, separate charges in space, and this electric polarization is dependent on the concrete type of director distortions. It has been introduced many years ago by Bob Mayer, and that means that the flexoelectric polarization caused by the curvatures of the director field can interact with the applied electric field and create a torque on the director. And the fact that it is the flexoelectric effect that creates the director bullets and drives them is supported by the fact that the director couples linearly to the applied electric field and oscillate in the vertical plane with the same frequency as the applied electric field. If you compare the estimate for the pulling force acting on the solitons with the viscous drag, you might find that the two things give approximately the same value, namely that the applied voltage that we use in the experiment is sufficient for a typical pneumatic lead crystal with the typical flexoelectric coefficient to create the force that is being compensated by the drag force. One question is, the electric field defects, as I demonstrated, have been studied in lead crystals since 1920s, 90s, 30s by Fredericks and then by many, many other people. So the question is why no one seen these soliton formations. One possibility is that not only the material should be of negative dielectric anisotropy to cancel this dielectric response, but also that the material must be sufficiently pure. In our case, the lead crystal that we are using is about 1 order of magnitude purer than the commercial lead crystals used in displays. The concentration of ions is really small by 1 order of magnitude. And it's probably the reason why this flexoelectric polarization is not immediately screened by the ions in the material. And this is probably the reason why other people didn't see these solitons. So I conclude with the observation that pneumatically crystals can produce and sustain three-dimensional solitonic excitations, three-dimensional director bullets, as we call them. They propagate quickly perpendicularly to the field and to the director. They interact and show either attraction or repulsion. There are many interesting properties that I briefly described, but the main point of interest probably for this audience is that there is no theory yet of the formation of these particles. There is no theory that would explain what is the nonlinearity that cancels the dispersion in the medium, and how these perturbations become stable. Why do they move with the huge speed that we observe? And maybe it would inspire someone here to work on the problem. Thank you very much for your attention. We are approaching electrohydrodynamic instability that occurs everywhere. So now the perturbations are not localized. They are just essentially everywhere. It's the well-known pattern of stripe domains. Yeah, here. That typically this pattern occurs immediately from the uniform state in many other Lie crystals. So if you have some conductivity, then it's like a Rayleigh-Benard thermal instability only caused by the motion of ions through the viscous medium that produces stripes. And these stripes are kind of visible here. It's a chaotic pattern of stripes. What is important is that between the uniform state and this stripy state, there is an entire range of voltages in which you have localized, well-localized excitations, the three-dimensional solitons. So this is the novelty of this work, this intermediate state. Yeah, they would disappear. It's as if you would look at this pattern in the reverse order. So first you would notice that their number is down, down, and then there is nothing. Just uniform state. Yes. Well, not in details. We understand, in general terms that when you collide two director perturbations, they need some time to reconstruct themselves, and that time depends on the viscosity of director reorientation. We know the numbers there, and we know how long would it take, and it appears to be consistent with the observations, but we don't have the exact theory even for the single soliton existence, not even going to the issue of their interaction. You can say that they have positive and negative velocity and symmetry. So the original background is with the director being vertical. And now the solitons are representing deformations that are bulged up or down with respect to the uniform state. So this is the original state. One soliton goes like this, and its counterpart goes like that. And they propagate in different directions, determined by whether it bulges up or down. In that sense, they are plus and minus solitons, but there is no topological charge. It's strictly zero. Practically any director deformation causes the flexoelectric polarization. It's easy to understand from this picture. If the director is uniform, then these shapes can be looking to the left and to the right with the same probability. The dipoles would kind of cancel, compensate each other. But if you have a band like that, so then more banana-like molecules will be looking with the dipoles to the right, and that would create this blue arrow of flexoelectric polarization. It's a pure geometry. And this is the material constant that characterizes these dipoles, essentially. It can be also explained in terms of quadrupoles. Yeah, but see, as I explained, when this director goes up and down, the azimuthal direction is not changing the sign. So the director does this thing. Goes up and down. This bulge goes up and down, and that's it. The counterpart does the same thing, but in the opposite direction. It's not a motion like this. It's a motion in the vertical plane. It's like rowing. It's a uniaxial nematic. There is nothing else there to look for. It's just a uniaxial nematic. We think it's a spontaneous deformation that is being reinforced by the applied electric field. So it occurs spontaneously, there is a polarization, and then the electric field shows up, and so they couple to each other, and then the electric field drives this vector up and down. The director does this, and because of that it propagates. Qualitatively. It's just a hand-waving argument.
Structure of topological defects in hexagonal manganites.
Talk, I will focus on the topological defects in a particular class of materials, this so-called multiferroic hexagonal manganites with this chemical formula. And what I will present here is base. Well, it doesn't work. Okay. There is a problem here. This one, yes. Okay, doesn't matter. So, it doesn't work at all. Okay, sorry. So what happens? So what I will present here is the result of the input of various people, in particular Megan Holt, PhD student at Cornell, in the group of David Muller, Kostya Shapovalov, my former postdoc in Bordeaux, and Quentin Mayer and Martin Lilienblum, PhD students at ETH Zurich. So as I said, I will focus on the topological defects that are observed in this class of materials. These defects are structural domain walls and structural vortices, and I will discuss the morphology of these topological defects in detail, and I will show you in particular that this type of vortices, structural vortices, develop an emergent U1 symmetry, so that in contrast to Rame's vortices, in this case, we can find an analogy between structural vortices and superconducting vortices. And then, if I have time, I will discuss also the formation of these topological defects that is believed to occur according to the so-called Kibble-Surek mechanism. First of all, I want to introduce the system of study is this hexagonal manganites. Here I show you the unit cell of the system in the high symmetry phase. As you can see, it has an hexagonal symmetry, and you find this manganese oxygen bipyramids, and here you have the rare earth atom in blue. So these systems are so-called improper ferroelectrics, in which the spontaneous polarization occurs as a result of the emergence of another order parameter. In this case, as we have shown in this paper, is the result of this type of distortion, in which what happens is that there are this rotation of the bipyramids and also the vertical displacements of the rare atom. And then, as a result of this distortion, there is a spontaneous polarization that we can interpret as a result of a coupling like this. Then the question is, what is this primary order parameter that produces this type of distortion and the trimerization of the lattice? So for this, and to develop the theory, we want to develop a theory that establishes a close contact with the experiments, and in particular with this kind of experiments. Here I show you an image obtained by scanning tunneling electron microscopy, in which we can see this distortion with atomic resolution. And then in this type of experiments, we see the heavy atoms, the manganese here in this line, also the rare earth, and as you can see, the rare atom displays this type of pattern. One atom is going up, the second up, and then down, so a pattern like this. But here we don't see the oxygen atoms, and therefore we cannot see this rotation of the bipyramids. So then we can parameterize this trimerization, trimerizing distortion according to this formula, and it's quite natural to define the order parameter of the transition according to this. So I will take in the following the order parameter of the trimerization as this quantity Q that defines the amplitude of this trimerization, and this phase phi here that I can compare directly with this type of experiments. So this is my definition of the order parameter, and then I can construct the Landau free energy. So here I show you the expression of the Landau free energy. I think this is the canonical expression of the Landau free energy, in the sense that it is expanded in terms of the order parameter and nothing else. So implicitly, all the rest of degrees of freedom are integrated out here. They don't appear explicitly here in this expression, but still we can compute the coefficients of this free energy, for example, from ab initio calculations. What we need to do is to impose this type of distortion, and then to compute the energy, the change in energy of the system according to this. But we need to let all the rest of degrees of freedom to relax and find the state of equilibrium. This B is not necessarily small. So why? Why are you asking? Well, this sixth order term, I agree with you that is strictly speaking not necessary, but this other one, it is. Okay, that is another story. This is very important to keep, because actually this is related to the hexagonal symmetry of our system, and because of this, we obtain 6 trimerization domains. So this term is essential for us. So as a result of this term, the energy landscape look like this. We find 6 different minima. Each of these minima correspond to one domain. And for example, if the C prime parameter is positive, so we find discrete values of this of the phase of the order parameter according to these 6 minima that we have here. Okay, so this is about the domains, but the purpose of this is to discuss topological defects. What kind of defects or excitations? So we have essentially 2 types. We have domain walls, when domain walls that corresponds to a path in ordered parameter space from one minimum to the next. And we can have also vortices if you continue this path and close the loop, so that the phase of the order parameter increases by 2 pi. So here I show you 2 images of, with again atomic resolution of 2 domain walls. Here the polarization is always vertical in this image. Here we have a sort of a standard 180-degree polarization domain wall that is neutral. And here is something more unusual, and is specific of this type of material. We have a charged domain wall in which the polarization is pointing in the same direction, but here we have a configuration that is tail to tail. So there is a bound charge that is accumulated to this wall. The important thing is the trimerization order parameter, and here the colors in the image corresponds to the value of the phase of the trimerization order parameter that we obtain fitting these displacements according to the formula that I showed you before. Then the first thing to notice is that, okay, here we have 2 domains. Here is a red domain, and here is a green, I would say green domain. And the transition from one domain to the other, in both cases, is not abrupt, but is more continuous. So this is the first thing that we notice doing this type of analysis, because otherwise you may conclude that the domain wall is very sharp. And actually there are papers, you can find papers in the literature, claiming that this type of domain walls in these materials are atomically sharp, whereas doing this analysis, you can easily see that this is not the case. Okay. What we wanted to do is to reproduce this type of domain walls without theory, and then the thing to do is to derive the Euler-Lagrange equations from the free energy, and solve this equation for this domain wall geometry. This is something that can be done analytically, and here you have the solution. This is the distribution of the phase of the order parameter as a function of the position. It has this formula, and this is obtained in the approximation of a constant amplitude of the order parameter. But this approximation can be improved in a sort of perturbative approach, and this is the correction that you get to this approximation. Here this is the profile of the amplitude of the trimerization order parameter. We can compare this to the experimental results. Here I show you the points correspond to the experimental data, and the lines are the fittings according to this formula. So this is the phase as a function of the position across the domain wall for different orientations of the domain wall. And here I show you the amplitude of the trimerization or the parameter as a function of the position. As you can see, this simpler these are essentially okay. This is the the notation. So these are essentially the two correlation lengths that appear in the problem. Here, for this theory, we find two characteristic lengths. One is the correlation length associated to the amplitude, to the amplitude of the order parameter. But here, because of the two-component character of the order parameter, there is a second correlation length associated to the phase. And it is this second correlation length that is linked to the anisotropy term in the free energy. That is the most important quantity for this type of domain walls, because by definition, these are domain walls in which the phase changes from 0 to pi/3, for example. So this is what we learn precisely from this exercise. As I said, in this system, we can have more complex topological defects. We can find also vortices. Here I show you an image of one of these vortices. Once again, the different colors correspond to different values of the phase of the order parameter, and I hope that you can see here different regions. So here, for example, we have a green region. Here is yellow, red, violet, and so on. So here we are in the domains, but there is this singular point at which the different domains merge. So here we have domain walls, and this is a singular point associated to the vortex. Here we have a vortex configuration. To see this, we can plot the phase of the order parameter along this path, and then if you are far enough from the singular point, you find this step-like behavior, because the domain walls are well defined, so that you see the discrete symmetry of the system. So here, the phase as a function of the angle around this loop behaves like this. You see that there are steps in which the phase of the other parameter increases. But the interesting thing here is that as you move closer to the center of the vortex, then the phase of the order parameter doesn't show this step-like behavior anymore. Then it simply increases linearly as a function of the angle around this loop, which means that in this region, we don't see the discrete symmetry breaking of the system anymore. So what we observe here is the emergence of a continuous U1 symmetry. And it is because of this that the vortex in this region becomes totally analogous to a superconducting vortex. So the phase of the order parameter in particular behaves like this as and displays this divergence. So this becomes a singular point, exactly as in superconducting vortices. Actually, the analogy works not only for the phase, but also for the amplitude of the order parameter. Here I show you the same data, but now the colors correspond to the value of the amplitude of the trimerization. So here we have the singular point. So this is the result of a simulation where we can see better this singularity. And this is the value of the amplitude of the trimerization as a function of the position of the distance to this singular point. So this the behavior, the experimental behavior that we find for the amplitude of the order parameter is again as in the case of superconducting vortices. So one interesting thing that we learn from this simple exercise is that this topological defect, so the morphology of this topological defect, is essentially determined by two correlation lengths. There is the standard correlation length associated with the amplitude of the order parameter, but there appears a second correlation length due to the sixfold anisotropy of the problem, and something that is generic for this type of problems is that the behavior as a function of the temperature, for example, is very different. In particular, this second correlation length diverges faster than the correlation length for the amplitude, and also the behavior with respect to the anisotropy term is very different. So we can easily arrive to a situation in which this second correlation length is much larger than the first one. If this happens, then we are in the U1 region, in which we lose the information about the sixfold symmetry breaking, and then this emergent U1 symmetry will dominate the properties of these topological defects. And then, again, they become totally analogous to superconducting vortices. So what kind of properties can we expect? So, for example, for the domain walls, it has been found in this paper that we can have enhanced conductance, and this can be explained very easily. For example, in the case of in which we have polar domains, because this depends on the anisotropy term. In the case in which we have polar domains, this is the profile that we find for the spontaneous polarization. It goes to 0 at the domain wall, but since the system is uniaxial, as a result of this dependence, there appears in general a bound charge localized at the domain wall, and then since the system is a semiconductor, this produces an enhancement of the local conductance at the domain wall. So this is now quite well established in the case of polar system. Something that has not been studied so far is that also in the case in which the domains are non-polar, so there is no spontaneous polarization within the domains, at the domain walls we will find a non-zero polarization resulting from the variation of the trimerization or the parameter, and the bound charge looks like this. So in this case, even in this case, we have a domain or domains that are non-polar, but the domain wall is a sort of ferroelectric thin film, because there emerges this spontaneous polarization localized at the domain walls. So very likely the domain walls, the ferroelectric domain walls in the non-polar hexagonal manganese will display new properties associated to this localized polarization, negative capacitance, or I don't know. So this was for the domain walls, but also the vortices. the vortices, can display new properties, that will be universal near the core of the vortices, because in this region, as I said, there emerges a universal U1 symmetry. And then if we compute the electric polarization and the bound charge resulting from this spontaneous polarization in this region, then we find a distribution of bound charge that looks like this. It has a sort of orthopolar character, and this is the case for both systems with polar ferroelectric domains and non-polar domains, because inside this U1 region, the two cases become equivalent. So in this sense, the properties that we can find associated to this will be universal. So now I move to the question of the formation, the formation of this type of topological defects. So now we are going to study the problem at a different length scale, more mesoscopic. So here the typical length scale is about a micron. Here I show you an image obtained by piezo response force microscopy, in which you can see the vortices here and the domain walls in these regions. And the question is, what do we need to do to the system to produce these topological defects? So the answer to this is simple. Actually, we don't need to do anything special, because this type of vortices and domain walls appears spontaneously as we drive the system across the phase transition from the high symmetry phase to the low symmetry phase. So here I show you different images that are obtained for two systems, the dysprosium compound and the erbium one. So and the different images correspond to different cooling rates for the quenching. As you can see, it is unavoidable, the formation of the topological defects, but the interesting thing to notice is that there is a correlation between the density of the defects that is produced and the cooling rate of the quenching. So the results are summarized here for different compounds. So here I show you the vortex density as a function of the cooling rate in a log-log plot. And okay, and as you can see, there is some scaling law behind this finding. So this has been interpreted in terms of the Kibble-Surek mechanisms. The Kibble-Surek mechanism was originally proposed to explain the possible formation of cosmological strings in the early universe, but it can be applied also to condensed matter system, and in this context, the Kibble-Surek mechanism has a very natural interpretation. It's nothing but the result of the critical slowing down of the system as we approach the critical point. So in general, the relaxation time of the system as we approach the critical temperature increases and formally diverges, as I showed you here. So then, as a result of this divergence, this means that as we approach the critical point, the system needs more and more time to find the state of equilibrium. Then it's sort of evident that no matter how slow we perform the quenching across the phase transition, there will be a time at which the system won't be able to find the new state of equilibrium. So then it will be frozen out, and we can distinguish two regimes. The adiabatic regime, in which the system can follow our external perturbation, and this frost out regime in which the system is out of equilibrium. Then the Kibble-Surek mechanism postulates that the vortex density that results that we observe as a result of this quenching is determined by the correlation length of the system evaluated at this freezing time. Then what we expect is a scaling law according to this formula, in which we have here the critical exponents nu for the correlation length and set for the this is the dynamical critical exponents, and tau is related to the cooling rate. Tau naught and xi naught are microscopic parameters. So this can explain this type of scaling. The question is, which exponents do we use in this formula? Because in general, there are two values for these critical exponents. If the fluctuations are Gaussian, we are in the mean field regime, and we have one set of values. But if the fluctuations are strong, then we are in the scaling region, and the value of these critical exponents are generally different. The answer to this question is the so-called Ginzburg-Levaniuk parameter that determines the crossover between the two fluctuation regimes, the mean field regime and the Ginzburg regime. So we estimated this Ginzburg parameter from the coefficients of the theory that we obtained from DFT calculations, and what we found is that this type of materials in this type of experiments are in the actually in none of those regimes. They are in the crossover between mean field behavior and scaling behavior. That means that these exponents that we have here probably are changing. They are running exponents. So we can find a situation like this. For very low cooling rates, we have one set of critical exponents like this. For high cooling rates, we are more in the mean field regime. We need to use another set of critical exponents. But not only this, also the microscopic parameters are renormalized due to critical fluctuations. These are subdominant corrections that normally you ignore if you are interested in the critical behavior. But in this problem, those corrections are relevant. So we can have a situation in which there is this offset, and then if the crossover region is narrow enough, we can have this drop down of the vortex density as a function of the cooling rate, and this can be an explanation for the behavior that we observe here experimentally at high cooling rates. So with this, I finish, and I thank you for your attention.